Chapter 1, The Cosmic Beginning. Close your eyes. Take a slow breath. Now imagine absolute darkness. No stars, no planets, no time, no space, nothing. That was the universe before it all began. And then, in an instant, everything changed. Around 13.8 billion years ago, something extraordinary happened. Something that would set the stage for galaxies, for stars, for life, and for you. This moment is called the Big Bang. Now let's slow it down. Let's understand what really happened, gently. The Big Bang wasn't an explosion in space. It was the sudden, rapid expansion of space itself. From a tiny, hot, dense point, smaller than a grain of sand, the universe began to grow. It stretched, inflated, and expanded faster than the speed of light. Time began. Space began. And so did everything else. In the first few seconds, the universe was unimaginably hot. Temperatures soared to billions of degrees. In that early fireball, the building blocks of matter were born. Protons, neutrons, electrons. These are the tiny parts that will one day make up atoms, and later, stars, planets, and you. But let's not rush ahead. Let's stay in those first few minutes after the Big Bang. As the universe cooled down a little, something beautiful happened. The first atomic nuclei formed, mostly hydrogen and a little bit of helium. This process is called nucleosynthesis, the creation of new atomic nuclei. But that was all the universe could make at the time. Just hydrogen, just helium, no carbon, no oxygen, no iron, none of the heavier elements that we are made of. Those were missing. So where would they come from? The early universe kept expanding and cooling. Galaxies formed, stars were born, and in the hearts of those stars, something miraculous began. But we'll get to that later. For now, just remember this. You are made of atoms, and those atoms were shaped by events that began 13.8 billion years ago. Every cell in your body, every beat of your heart, every breath you take, has a story that began in the fire of the Big Bang. Isn't that astonishing? And here's something even more humbling. The hydrogen in the water you drink, the helium that fills balloons, the atoms in your body all trace their origins to that early moment in time. They have traveled through time. They have seen the birth and death of stars. They have floated in space, and now they are you. You see, the universe didn't just create the stars. It created the ingredients for life. But at this point in time, the young universe was still simple, mostly dark, mostly cold, waiting for something more. And so the story continued. Gravity, the quiet force that pulls things together, began to work. It started to clump hydrogen and helium into great clouds. These clouds slowly collapsed, pulling atoms closer and closer until they lit up. The first stars had been born. And inside them, the next part of your story began, because those stars were the first factories of elements. In the next chapter, we'll journey into their hearts. We'll witness how stars act as cosmic ovens, forging new elements in their blazing cores. But for now, sit with this thought. You are connected to the beginning of everything, to the great cosmic unfolding that began 13.8 billion years ago. You are not separate from the universe. You are its child. You are made of stardust, and the story is just beginning. Chapter 2. The Alchemy of Stars, How Elements Are Forged in Stellar Cores. When we look at the night sky, it's easy to think of stars as distant pinpoints of light. But in reality, each star is a massive, complex machine, a nuclear furnace operating under extreme conditions. And these stars are far more than just lights in the sky. They are responsible for producing most of the elements that make up everything around us, including our own bodies. In this chapter, we will explore exactly how stars create the elements that eventually became the building blocks of life. This process, known as stellar nucleosynthesis, is the key reason why we say we are made of stardust. Let's begin by understanding what stars are made of and how they are formed. The birth of stars. A star begins its life inside a giant molecular cloud, a cold, dense region of space filled with hydrogen gas and dust. These clouds are scattered throughout galaxies and can be hundreds of light years across. At some point, due to disturbances such as shock waves from nearby supernovae or gravitational interactions, parts of these clouds begin to collapse under their own gravity. As the gas contracts, it heats up, and the center of the collapsing region forms a protostar, a young star that is not yet hot enough to initiate nuclear fusion. As gravity continues to pull the material inward, the temperature and pressure in the core of the protostar increase. Once the core reaches about 10 million degrees Celsius, hydrogen nuclei begin to fuse together. This marks the beginning of the star's life on what astronomers call the main sequence. Nuclear fusion, powering the stars. The main source of energy in a star comes from nuclear fusion. In the simplest and most common fusion reaction, which occurs in stars like our Sun, 4 hydrogen nuclei, protons, combine to form one helium nucleus. This process releases an enormous amount of energy. What's fascinating is that during this reaction, a tiny amount of mass is lost. According to Einstein's equation, E is equal to mc squared, that lost mass is converted into energy. Energy that powers the star and produces the light and heat we receive on Earth. For millions or even billions of years, stars remain stable, balancing two forces, gravity pulling inward and fusion-generated pressure pushing outward. As long as hydrogen is available in the core, the star can maintain this balance. But hydrogen doesn't last forever. The creation of heavier elements. Once a star uses up the hydrogen in its core, it begins to undergo dramatic changes. In stars that are much more massive than our Sun, the core contracts and heats up further, allowing helium fusion to begin. Helium atoms fuse to form carbon. As temperatures continue to rise, carbon can fuse to form oxygen, and then neon, magnesium, silicon, and other heavier elements. This process continues in layers, like the structure of an onion. The heaviest elements are at the center, with lighter elements in shells around them. This layered structure is typical of a massive star nearing the end of its life. The process of element formation inside stars is called stellar nucleosynthesis, and it is responsible for all the naturally occurring elements in the periodic table up to iron. But there's a limit. The iron barrier. Iron represents a turning point in the life cycle of a star. Unlike the fusion of lighter elements which releases energy, the fusion of iron consumes energy. This means that once a star begins to accumulate iron in its core, it can no longer generate the energy needed to support itself against gravitational collapse. At this stage, massive stars face a catastrophic end. The core collapses in a fraction of a second. The outer layers rebound off the dense core and are blown outward in a massive explosion known as a supernova. Supernovae, factories of the heaviest elements. Supernovae are some of the most energetic events in the universe. During a supernova explosion, the temperatures and pressures become so extreme that nuclear reactions occur rapidly and violently. In these brief but intense moments, elements heavier than iron, including gold, platinum, uranium, and lead, are formed through a process called neutron capture. These elements are then scattered into space, mixed into the interstellar medium, and become part of the raw material for the next generation of stars, planets, and eventually life. Our solar system and stardust. Roughly 4.6 billion years ago, one of these enriched clouds of gas and dust collapsed to form our Sun and the rest of the solar system. Embedded within this cloud were all the heavy elements produced by countless earlier generations of stars. The Earth formed from this material, a mix of metal, rock, and gas, forged in the hearts of stars and spread across the galaxy by stellar explosions. So when we say we are made of stardust, it is not a metaphor. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of these were created through stellar fusion or supernova explosions. The atoms in your body have literally passed through the interiors of stars. The evidence. You might ask, how do we know all this? Astronomers study spectral lines, the specific fingerprints of elements in light coming from stars. By examining the light from distant stars and galaxies, scientists can determine which elements are present. They can even trace the history of element formation across cosmic time. In laboratories on Earth, physicists have recreated the processes of nuclear fusion and measured the energy released in different fusion reactions. These experiments confirm the theories of stellar nucleosynthesis. We also find evidence in meteorites, which contain isotopes of elements that could only have been formed in supernova explosions or neutron star collisions. In short, the theory is supported by observational astronomy, laboratory physics, and the study of ancient cosmic material. Chapter 3. From Dust to Planets, the Birth of Earth from Cosmic Debris. Around 4.6 billion years ago, in a quiet arm of the Milky Way galaxy, something remarkable happened. A cloud of gas and dust, the remains of long-dead stars, began to collapse. This single event would eventually lead to the formation of our solar system, including Earth itself. But how does a planet like Earth, solid, rich in elements, teeming with life, emerge from a floating cloud of cosmic dust? To answer that, we must understand the sequence of events that connects star death to planet birth. Let's begin with what we call a solar nebula. The solar nebula, our origin cloud. After a supernova, the explosive death of a massive star, the resulting cloud contains not only hydrogen and helium, but also heavy elements like carbon, iron, silicon, and oxygen. These materials don't just disappear, they spread out across space. Over time, gravity starts to gather this material back together into a new cloud, the solar nebula. The nebula that would give rise to our solar system was likely triggered into collapse by a nearby stellar explosion. That disturbance caused a small region of the cloud to begin contracting under its own gravity. As it collapsed, it began to spin, slowly at first, then faster and faster, flattening into a rotating disk. At the center of this spinning disk, the bulk of the material gathered into a growing mass. This would become our sun. Surrounding it was a wide, thin disk of gas and dust, known as the protoplanetary disk. It is within this disk that planets like Earth began to form. From dust grains to planets. At first glance, it's hard to imagine how tiny dust particles can lead to the formation of a planet. But given enough time and the right physical conditions, even grains can evolve into worlds. Here's how the process works. 1. Coagulation. Small particles of dust stick together when they collide. This happens thanks to electrostatic forces, the same principle that causes static cling in laundry. These small clusters grow larger, forming pebble-sized aggregates. 2. Accretion. Over time, as these clusters collide and merge, they form larger bodies called planetesimals, rocky or icy objects a few kilometers in size. These are the seeds of planets. 3. Gravitational attraction. Once an object reaches a certain size, its gravity starts to play a major role. It pulls in nearby material, accelerating growth. This leads to the formation of protoplanets, Moon to Mars-sized bodies that begin to shape the architecture of the solar system. This entire process from dust to planetesimal to planet occurred over tens of millions of years. It was not smooth or orderly. Collisions were frequent. Some bodies grew larger, others were shattered or flung out of the system. Eventually, through a chaotic process of aggregation and violent impacts, a protoplanet formed in the region now occupied by Earth. Earth's violent youth. The early Earth was nothing like the blue-green planet we know today. It was a hot, molten world, constantly bombarded by leftover debris from the solar system's formation. Each impact added energy, heat, and new material. One of the most significant events in Earth's early history was a giant impact, a collision with a Mars-sized object. This impact was so intense that it ejected a large amount of material into orbit around the young Earth. That material eventually coalesced to form the Moon. After this event, Earth began to cool. The surface solidified, and a thin crust formed. Volcanic activity was intense, and the atmosphere was dominated by gases like carbon dioxide, methane, and water vapor. No oxygen yet. But within this hostile environment, conditions were being set for something extraordinary. The role of water and organic molecules. Water is essential for life as we know it. But where did Earth's water come from? Some of it was likely trapped in the minerals of planetesimals during Earth's formation. But much of it may have been delivered later by asteroids and comets, icy bodies from the outer solar system that collided with Earth, bringing with them water and organic molecules. Recent studies of carbon-rich meteorites have shown that they contain amino acids. the basic building blocks of proteins. This suggests that the seeds of life may have existed even before Earth fully formed. These ingredients didn't create life immediately, but they created the conditions where life could eventually arise, a concept known as prebiotic chemistry. Earth settles into stability. As millions of years passed, Earth continued to evolve. Gravity pulled heavier elements like iron and nickel toward the core, forming a layered planet with a dense metallic core, a mantle of molten rock, and a solid crust. Volcanic eruptions released gases into the atmosphere, slowly altering its composition. Meanwhile, water accumulated in basins, forming the first oceans. It's important to note that everything we see today, the continents, the oceans, the mountains, all come from the materials formed in stars. Silicon and oxygen make up the crust. Iron is in the core. Carbon is in every living organism. These atoms were forged in the nuclear furnaces of ancient stars, scattered in supernova explosions, gathered into a nebula, and eventually shaped into a planet capable of supporting life. The bigger picture. Let's pause and put this in perspective. You are walking on a planet made from stardust. Every rock, every tree, every molecule of water owes its existence to stellar processes that began billions of years before the Earth was born. What's even more remarkable is how common this story might be. Astronomers have discovered thousands of other planetary systems in the galaxy. Many of them have rocky planets, some even in the so-called habitable zone, the region where conditions might allow for liquid water. This suggests that planet formation is not unique to our solar system. It is a natural byproduct of star formation. Wherever stars are born, there is a good chance that planets form around them. And where planets form, the ingredients for life may not be far behind. Chapter 4: The Chemistry of Life: How Stardust Turned into Living Cells. Once the Earth had formed and cooled, and once oceans had collected on its surface, a new question emerged. How did life begin? Not in the form of complex organisms or multicellular creatures, but at the most fundamental level. How did molecules made of non-living atoms begin to assemble, organize, and replicate? This is where chemistry meets biology, a transition point known as abiogenesis, the origin of life from non-living matter. And the key to this transition lies in understanding how simple, star-forged elements became the molecules that define living systems. The building blocks life is made of 4 basic types of molecules: proteins, nucleic acids like DNA and RNA, lipids, fats and cell membranes, carbohydrates, sugars and energy sources. Each of these is composed of smaller units: amino acids, nucleotides, fatty acids, and simple sugars, all of which can be built from elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements, often abbreviated as CNOPs, are essential for life. They were formed in stars and delivered to early Earth through comets, meteorites, and interplanetary dust. Their presence on early Earth set the stage for prebiotic chemistry, chemical reactions that occur without life but lead to conditions that support life. The prebiotic soup. One of the earliest hypotheses for life's origin suggested that Earth's oceans were once filled with a rich mixture of organic molecules, a primordial soup. In the 1950s, this idea gained support when chemists Stanley Miller and Harold Urey conducted an experiment that simulated early Earth's atmosphere. They combined water, methane, ammonia, and hydrogen in a closed system, then applied electrical sparks to simulate lightning. After just a few days, the experiment produced several amino acids, the basic components of proteins. This experiment showed that under the right conditions, the building blocks of life can form spontaneously from simple chemicals. While we now believe Earth's early atmosphere was different from what Miller and Urey assumed, the underlying principle remains sound. Organic molecules can form from inorganic chemistry, and these molecules didn't just float randomly in water. Concentration and organization. For life to begin, molecules needed to concentrate and interact in ways that encouraged complexity. Several mechanisms may have helped. Evaporation pools, where water periodically dried up and left concentrated chemicals behind. Hydrothermal vents deep in the ocean where hot mineral-rich fluids flow from beneath the seafloor. These environments offer heat, energy gradients, and chemical diversity, ideal conditions for reactions. Clay surfaces, which can help organize and catalyze reactions by holding molecules in place. Wherever it happened, certain combinations of molecules began to perform useful functions, storing energy, forming protective barriers, or copying themselves in primitive ways. This marked the beginning of chemical evolution, the gradual improvement of molecular systems through natural processes, long before life existed in any form we'd recognize today. Self-replication. One of the most critical features of life is the ability to replicate, to make copies of itself. Without replication, evolution cannot occur and life cannot persist. Scientists believe that the first replicators were RNA-like molecules. RNA, or ribonucleic acid, is a cousin of DNA. It can store information like DNA, but also perform chemical reactions like enzymes. In fact, certain types of RNA can catalyze their own replication under the right conditions. This dual functionality has led to the hypothesis of an RNA world, a stage in early evolution when RNA molecules acted both as genetic material and as molecular machines. In this world, RNA molecules that were better at replicating would outcompete others, leading to increasingly complex systems. Eventually, these systems gave rise to more stable genetic codes based on DNA and more efficient catalysts, proteins. Membranes and cells. While molecules could form and interact in water, life as we know it requires a boundary, a place where internal chemistry is separated from the outside environment. This is where lipids come in. Lipid molecules have one end that's attracted to water and another that repels it. When placed in water, they spontaneously form membranes, thin, flexible structures that resemble modern cell walls. In laboratory experiments, scientists have shown that these membranes can form vesicles, small bubble-like containers, which can trap molecules inside. Over time, these vesicles could grow, split, and enclose replicating RNA, forming protocells, simple versions of cells. At this point, the essential systems of life were in place. Molecules could store and copy information. Catalysts could speed up chemical reactions. Membranes could create compartments for specific processes. All of this occurred without direction, without a blueprint, only through chemistry, probability, and time. Energy and metabolism. Life also needs energy. Modern organisms use complex systems to extract energy from food or sunlight, but early life likely relied on simpler methods. Some theories suggest that life began in hydrothermal vent systems, where hot, chemically reactive water provided a constant source of energy. Others propose that light from the sun drove early chemical reactions in shallow pools. Regardless of the energy source, some molecules developed the ability to drive reactions that supported growth and replication. This gave rise to metabolism, the coordinated set of chemical reactions that sustain living systems. From chemistry to biology, at some point the transition occurred. What had been complex chemistry became the first cell, a living, evolving system. This cell could grow, divide, pass on its structure, and adapt to its environment. It was not conscious, it was not complex, but it was alive. It may have looked nothing like modern cells. It may have used RNA instead of DNA. Its membrane may have been fragile, its reactions slow, but it marked the beginning of biology on Earth. From this point, evolution took over. Through mutation, selection, and time, these early cells diversified. They became more efficient, more resilient, and more complex. Eventually, they led to everything we now consider living: bacteria, plants, animals, and us. Chapter 5. The Evolution of Complexity, from single cells to sentient beings. Life began as simple, but over billions of years, it became complex. Today, the planet is filled with organisms of astonishing variety, some invisible to the naked eye, others towering across landscapes. Some drift passively in oceans, others walk, think, build, and explore. The leap from basic, single-celled life to intelligent, multicellular organisms like humans was not sudden. It was slow, methodical, and governed by one principle: evolution by natural selection. This chapter explains how complexity arose, not from design, but from gradual adaptation over immense timescales. Cellular innovation, the rise of eukaryotes. For more than 1 billion years, life on Earth consisted only of prokaryotes, simple single-celled organisms like bacteria and archaea. These cells are small, with no internal compartments. Their DNA floats freely in the cytoplasm, and they reproduce by splitting in two. The next major step was the emergence of a new kind of cell, the eukaryotic cell. Eukaryotes are larger and more structured. They contain internal organelles, compartments with specialized functions. Most importantly, they have a nucleus which houses DNA inside a membrane. How did this change happen? The leading theory is endosymbiosis. According to this idea, some ancient cells engulfed others, not to digest them, but to live with them. Over time, these internal partners became permanent residents. For example, mitochondria, the powerhouses of our cells, likely originated as free-living bacteria that were absorbed and adapted for energy production. This fusion allowed cells to do more. With organelles managing energy, waste, and reproduction, eukaryotic cells could grow larger and carry out more complex processes. Eukaryotes became the ancestors of all fungi, plants, and animals. The leap to multicellularity. The next leap in complexity came when individual cells began to cooperate, forming colonies, then integrated organisms made of many cells. This was not simply a matter of cells sticking together. It required communication systems between cells, differentiation, where cells specialized in different roles, coordination to control growth and repair. Multicellularity allowed organisms to build bodies with tissues, organs, and systems. Some cells focused on structure, others on movement, digestion, or reproduction. This division of labor increased efficiency and resilience. The fossil record shows that multicellular life began appearing over 600 million years ago. One of the earliest known complex organisms is Dickinsonia, a flat, segmented creature that lived in shallow marine environments. These early forms were soon followed by an explosion of diversity. The Cambrian explosion. About 540 million years ago, life experienced a dramatic burst of innovation in a relatively short geological period, an event known as the Cambrian explosion. In this time span, roughly 20 to 25 million years, most of the major animal body plans emerged. Arthropods with jointed limbs and exoskeletons, mollusks with soft bodies and shells, chordates with a notochord, the precursor to spinal columns. This rapid diversification may have been triggered by changes in oxygen levels, genetic innovations, or new predator-prey dynamics. For the first time, ecosystems became complex, with food webs, habitats, and competition. The groundwork was laid for larger, more specialized organisms, and for the eventual rise of vertebrates. From water to land, fish were the first vertebrates, animals with backbones. Their skeletons provided support, and fins allowed movement. Over time, some fish developed limb-like structures, better adapted for shallow waters and muddy bottoms. Roughly 375 million years ago, a lineage of these fish began venturing onto land. One key fossil from this transition is Tiktaalik, which shows both fish and amphibian features, gills and scales, but also robust limbs and a neck. The movement onto land required major adaptations: lungs for breathing air, stronger limbs for support, skin to prevent water loss, new reproductive strategies like laying eggs with protective shells. From this point, life diversified further into amphibians, reptiles, birds, and mammals. The mammalian blueprint. Mammals evolved from reptile-like ancestors about 200 million years ago. Their defining traits, warm-bloodedness, hair, and live birth, gave them flexibility and survival advantages. When a mass extinction wiped out the dinosaurs 66 million years ago, mammals rapidly diversified. With fewer competitors, they occupied forests, oceans, and grasslands. Some mammals developed large brains and social behavior. These traits were especially pronounced in primates, the group that includes monkeys, apes, and humans. The emergence of humans. About 6 to 7 million years ago, human ancestors began walking upright in Africa. This freed their hands for tool use and changed how they interacted with their environment. Over time, early hominins evolved into different species. One of the most significant was Homo habilis, known for using stone tools. Later came Homo erectus, who spread from Africa to Asia and Europe. The most recent lineage is Homo sapiens, modern humans, appearing roughly 300,000 years ago. Key traits distinguished Homo sapiens: advanced language and communication, complex tools and art, cooperative hunting and food sharing, long-term memory and abstract thought. These abilities allowed humans to form cultures, pass down knowledge, and reshape their environment. No other species had done this at such a scale. Consciousness and reflection. As brains grew larger and more complex, something else emerged: self-awareness. Humans began to think not just about survival, but about existence. They looked at the stars, told stories, invented gods, and asked questions. Art, religion, and philosophy appeared. What is remarkable is that all of this, the mind, the imagination, the curiosity, came from a long chain of events that began with molecular evolution, guided by natural laws. Your ability to think, to love, to wonder, it is the latest expression of complexity that began billions of years ago in the ocean, with single cells. Chapter 6: The Human Body, a Stardust Blueprint. The human body is often perceived as something mystical, a complex machine, a sentient being, a vessel of awareness. But at its foundation, it is simply an arrangement of elements. What makes that arrangement extraordinary is not just its structure, but the cosmic origin of its components. Your body is a meticulously arranged collection of atoms, each created through ancient nuclear reactions, many dating back billions of years. This chapter explores the chemical composition of the human body and follows each of its elements back to the stars from which they were born, the dominant elements in you. Though the biology of the human body is intricately detailed, it is primarily composed of only a handful of elements. These were not chosen at random by evolution. Rather, they were selected from what the universe made available when and where life emerged. Let's explore the key elements that form the structure of your body. 1. Oxygen, 65%. Oxygen is the most abundant element in your body. Although we typically associate oxygen with breathing, most of it exists within water, which accounts for roughly 60% of your body's weight. Oxygen is also present in proteins, DNA and RNA, sugars and fats, bones and cartilage. These oxygen atoms were created in the cores of massive stars during the final stages of their nuclear burning. When those stars exploded in supernovae, oxygen was hurled into the cosmos, eventually becoming part of planets, oceans, and life. 2. Carbon, 18%. Carbon is the essential foundation of all organic matter. Every protein, sugar, fat, and nucleic acid in your body is structured around carbon. Carbon is unique in its ability to form 4 covalent bonds, which allows it to construct a wide range of molecules, including rings, chains, and complex branching structures. Carbon was synthesized in red giant stars through the triple alpha process, in which 3 helium nuclei fuse to form a carbon atom. 3. Hydrogen, 10%. Hydrogen is the lightest and oldest element in your body, formed just minutes after the Big Bang, long before stars existed. In your body, hydrogen is primarily found in water molecules, organic compounds like fats and proteins, acids and enzymes. Despite its minimal mass, hydrogen plays a critical role in energy transfer and in stabilizing the structure of molecules vital for life. 4. Nitrogen, 3%. Nitrogen is a crucial element in amino acids, the building blocks of proteins, as well as in nucleotides, which form DNA and RNA. Without nitrogen, life could neither construct new cells nor pass on genetic information. Nitrogen is created in the explosive ends of intermediate mass stars and is distributed through space in gas clouds. These clouds later become the raw material from which new star systems form. 5. Calcium, 1.5%. Calcium gives your body its strength and support. The majority of it is stored in your bones and teeth, forming a rigid framework that protects and moves your body. It also plays a vital role in muscle contraction, nerve function, blood clotting. Calcium originates in the powerful fusion reactions during supernovae, where conditions generate elements heavier than oxygen. 6. Phosphorus. Phosphorus may be less known, but it's absolutely essential. It's a key structural component of DNA and RNA and is also vital to ATP, the molecule that provides energy for nearly every process inside your cells. Phosphorus enables energy transfer, metabolic regulation, and cell formation. Like many elements in your body, phosphorus is a result of stellar nucleosynthesis, released during the deaths of massive stars and embedded into planets forming from stellar debris. Other key elements, potassium and sodium, regulate electrical activity in muscles and nerves. Magnesium supports enzyme reactions and stabilizes genetic material. Iron, integral to hemoglobin, the oxygen-carrying component in red blood cells. Sulfur, found in certain amino acids and helps maintain protein structure. Each of these elements fulfills a specific biological function and all trace their origin to stars. The periodic table in you. If you were to sort the atoms in your body by element, you'd discover around 60 different types, about 1/4 of all known elements on the periodic table. Among them are essential trace elements such as zinc, important for immune health and enzyme function; copper, required for proper handling of iron; selenium, protects cells from oxidative stress; iodine, necessary for producing thyroid hormones. Though they account for only a minuscule portion of your body's mass, these elements are essential for survival, and none of them were made within your body. Every atom was formed in a celestial event, long before Earth ever came into being. How did they get here? Once born in stars, these elements were flung across space. Some were swept away by stellar winds, while others were expelled during supernova explosions. They traveled through interstellar clouds, mixing and cooling over millions of years. Eventually, gravity pulled these clouds together to form new stars, and from the leftover debris, planets emerged. Earth was one of those planets. Over the ages, geological processes, atmospheric chemistry, and extraterrestrial impacts delivered these elements to Earth's surface, where they became available to living organisms. As life evolved, it learned to harness these elements in increasingly sophisticated ways. Evolution didn't invent chemistry. It inherited and optimized the chemistry of the stars, and today that stellar chemistry continues within you. The body as a cosmic archive. Your body is a living artifact of cosmic history. The hydrogen in your tissues is older than the sun. The iron flowing in your veins was formed in a dying star. The calcium in your skeleton once resided in the furnace of a collapsing star. Every breath you take and every beat of your heart depends on atoms that have crossed unimaginable distances and timescales. You are not merely surrounded by stardust. You are made of it. Your body's systems, circulatory, nervous, muscular, are composed of elements born in stars. But unlike stars, which burn out and collapse, these atoms in your body have taken on a new form, alive, aware, and interconnected. With every passing moment, your life continues the cosmic narrative, not as a spectator, but as a living participant. Chapter 7. Life Beyond Earth, Searching for Stardust Elsewhere. We now know the universe is filled with the ingredients of life, but is Earth the only place where those ingredients came together to form something living? This question is no longer confined to science fiction. It is a major field of scientific inquiry known as astrobiology, the study of life in the universe. This chapter examines where, how, and why scientists are searching for life beyond our planet, and what clues the cosmos is already giving us. Building blocks beyond Earth. The search begins with chemistry. Telescopes aimed at distant star systems have detected complex organic molecules, the same kinds used by life on Earth, floating in interstellar clouds and on the surfaces of comets. Using spectroscopy, scientists have found amino acids, the building blocks of proteins, polycyclic aromatic hydrocarbons, carbon-based molecules, formaldehyde and methane, which are precursors to sugars and fats. These molecules are not rare. They form spontaneously under the right conditions, even in the freezing cold of space. This tells us that life's raw materials are widespread. But chemistry alone isn't life. For life to emerge, these materials must combine under the right conditions, with energy, water, and stability. So where might that happen? Habitable zones around stars. Scientists define a habitable zone as the region around a star where temperatures allow liquid water to exist on a planet's surface, not too hot, not too cold. Earth is in such a zone around the Sun. Astronomers have discovered thousands of exoplanets, planets orbiting stars beyond our solar system. Many of these lie within their stars' habitable zones. Some are similar in size and mass to Earth. Others are super-Earths, slightly larger but potentially rocky and temperate. By studying the light that passes through the atmospheres of these planets, researchers are looking for biosignatures, chemical fingerprints that may indicate life. These include oxygen and ozone linked to photosynthesis, methane, especially in combination with oxygen, water vapor, unusual patterns of carbon dioxide and nitrogen. Although no definitive biosignature has yet been confirmed, the tools are improving fast. Missions like JWST James Webb Space Telescope and upcoming telescopes like LUVOIR and HabEx are designed to detect Earth-like atmospheres across light years. Life in our own backyard. We don't have to look far to search for alien life. Some of the most promising candidates are within our own solar system. Mars. Mars once had rivers, lakes, and possibly even oceans. It still has frozen water under its surface, and possibly briny liquid water in some regions today. Robotic missions like Perseverance and Curiosity are examining Martian soil and rock layers for signs of ancient microbial life, including chemical patterns or fossilized bacteria. So far, there is no proof of life, but the planet remains one of the most studied candidates. Europa and Enceladus. These icy moons of Jupiter and Saturn, respectively, may be better places to search. Beneath their frozen surfaces lie global oceans of liquid water, kept warm by tidal heating, gravitational friction from their massive host planets. Both moons have plumes of water vapor erupting into space, allowing spacecraft to analyze their composition without even landing. These plumes contain salts, simple organic compounds, molecular hydrogen, which can feed microbial ecosystems. NASA and ESA are planning missions like Europa Clipper and Enceladus Orbelander to investigate these oceans more deeply. If life exists in these subsurface seas, it could resemble deep-sea organisms on Earth that survive without sunlight, using energy from hydrothermal vents. Titan, Saturn's largest moon, Titan, has lakes and rivers, not of water, but liquid methane and ethane. This alien chemistry suggests that life could exist in a completely different form, one that doesn't require water at all. The upcoming Dragonfly mission will land on Titan and study its surface for prebiotic chemistry or signs of exotic life. Alternative biochemistries. Most searches for extraterrestrial life are based on what we know, carbon-based life using water. But there's a growing awareness that life could look radically different elsewhere. Scientists are exploring possibilities like silicon-based life, life using ammonia or hydrocarbons as solvents, plasma-based structures in extreme environments, self-organizing systems made of entirely different compounds. While these remain hypothetical, they expand the scope of astrobiology beyond Earth-like environments. The Fermi paradox. One of the biggest mysteries is this: if the universe is teeming with habitable planets, where is everyone? This is the essence of the Fermi paradox, the contradiction between high estimates of alien life and the lack of evidence for it. Possible explanations include life is common, but intelligent life is rare. Civilizations may self-destruct before reaching interstellar capability. We may not recognize alien life when we see it. They may be avoiding us, or we're not listening on the right frequencies. Some scientists are looking for techno-signatures. Signals of technology, like radio waves, artificial light, or industrial gases in exoplanet atmospheres. Projects like SETI, Search for Extraterrestrial Intelligence, scan the skies for such signals. So far, the silence remains. Why this matters? The search for extraterrestrial life is not just about aliens. It's about understanding whether life is a common outcome of cosmic chemistry or a rare event. If we find life, even microbial, on another world, it means life is likely widespread across the universe. If we don't find it, even after exhaustive searching, that tells us something equally profound, that Earth may be extraordinarily rare, and life here is an outlier in cosmic history. Either way, the answer reshapes how we see ourselves. Chapter 8: Entropy, Order, and the Emergence of Life. In physics, the universe trends toward disorder. This principle is called entropy, a central concept in thermodynamics. Over time, systems naturally progress from organized, low-entropy states to more disordered, high-entropy ones. But life seems to break that trend. It builds order, it creates structure. Cells form, replicate, and evolve. DNA copies itself with remarkable fidelity. Organisms grow, adapt, and persist. At first glance, this appears to contradict the laws of thermodynamics. But when we look deeper, we find that life does not defy entropy. It is a product of it. This chapter explores how the tendency toward disorder actually drives the emergence of complexity, and how that process may have created life itself. The arrow of entropy. Entropy is often misunderstood as chaos, but in physics it refers more precisely to the number of ways a system can be arranged. A high-entropy state has many possible configurations, like gas molecules scattered in a room. A low-entropy state is more ordered, like a crystal or a tightly folded protein. According to the second law of thermodynamics, entropy in a closed system will always increase or stay the same. It never decreases on its own. In practical terms, heat flows from hot objects to cold ones. Energy spreads out unless it is constrained. Systems decay, erode, and break down over time. The universe is constantly moving toward higher entropy. Stars burn out, structures collapse, particles scatter. So how, in this context, does life, a highly ordered system, emerge? Local order in an entropic universe. The key lies in the word local. The universe overall trends toward disorder, but small regions within it can become temporarily more ordered as long as they increase entropy elsewhere. Life is one of those regions. Your body, for example, maintains an incredibly ordered state. It repairs tissues, builds proteins, and regulates temperature. But to do this, it must consume energy, usually in the form of food or sunlight. As it uses this energy, it releases waste heat and molecules, which increase entropy in the surroundings. So while life builds internal order, it obeys the second law by increasing entropy outside itself. This is how islands of order, like cells, plants, and brains, can exist within a sea of increasing disorder. Energy flow and complexity. Where there is a flow of energy, there is the potential for complexity. Planets like Earth, which receive energy from the sun and radiate it back into space, exist in a non-equilibrium state. They are constantly taking in and giving out energy. In such environments, chemical systems can evolve toward more efficient ways to handle energy. Sometimes, that includes forming self-replicating molecules or membranes that trap and organize materials. These systems, often called dissipative structures, are temporary but can grow in complexity. Famous examples include hurricanes, convection cells, crystal growth in chemical reactions. Life may have started as a kind of dissipative structure that accidentally became stable enough to evolve. In this view, life isn't a defiance of entropy, it's a natural response to energy gradients. It's a structure that forms because it helps the universe move energy from one place to another. Prebiotic chemistry and thermodynamic favorability. Before biology began, there was prebiotic chemistry, molecules forming in warm pools, mineral surfaces, or ocean vents. Not every reaction in these environments was likely, but some used energy in ways that produced more entropy in total, making them thermodynamically favorable. For example, organic molecules assembled in hot environments where heat helped drive reactions. Lipid-like molecules spontaneously formed bubbles, precursors to cell membranes. RNA-like molecules that could replicate used available energy to grow even if they were unstable. Over time, these chemical systems may have self-selected for reactions that not only built complexity, but dispersed energy efficiently, meeting the entropy requirement while forming increasingly structured networks. Life as an entropy engine. Some physicists now describe living systems as entropy engines, machines that operate by taking in usable energy, processing it, and returning degraded energy to the environment. Photosynthesis, respiration, and digestion all follow this principle. They start with low-entropy energy sources, sunlight, sugars. They convert these into high-entropy outputs, heat, carbon dioxide, waste. In doing so, organisms maintain their own internal structure, temporarily, while increasing entropy elsewhere. This thermodynamic view of life is reshaping biology, helping scientists understand not just how life works, but why it emerged. Evolution as an entropic process. Even evolution, the driver of biological diversity, follows the logic of entropy. Species evolve through random mutations and natural selection. Each generation spreads genes that survive better under local conditions. But at a molecular level, evolution is powered by energy flow and entropy. DNA replication uses ATP, releasing waste energy. Protein folding favors the lowest energy, most stable state. Organisms that better exploit energy sources spread more genes. So even as species become more complex, the universe as a whole moves toward higher entropy. Complexity does not fight entropy. It is a temporary state that arises because it helps move energy from concentrated to diffused states more efficiently. The role of the sun. Our sun is a massive engine of low-entropy energy. Every second, it pours energy onto Earth, creating the conditions for entropy gradients. Without the sun, Earth would be in thermal equilibrium with deep space, cold, still, and lifeless. But with the sun, Earth became a planet in motion, with winds, weather, oceans, and biology. The sun provides negentropy, localized, concentrated energy, which fuels the processes that make life possible. Eventually, the sun will die and Earth's entropy gradient will flatten. But until then, the energy flow continues, and life remains one of its most remarkable outcomes. Chapter 9: Death, Decay, and the Recycling of Stardust. All living systems, no matter how complex, eventually come to an end. Cells stop functioning. Organisms break down. Structures that took decades to build collapse within days or hours. But death is not destruction in the way we often think of it. It is not an end to matter, only a transformation. Your atoms, the very elements that make up your bones, blood, and brain, are not destroyed when you die. They are released, dispersed, recycled. This chapter explores what happens to those atoms after life ends, how they return to the earth, the air, the sea, and eventually the stars. Molecular breakdown begins. The moment biological processes stop, the body becomes part of the environment again. Decomposition begins quickly. Within hours, cells rupture, releasing enzymes that start digesting tissues from the inside. Bacteria, once kept in check by the immune system, spread freely. Proteins unravel. Membranes collapse, organs soften. This is not a disappearance. It is a breakdown of biological structure into simpler molecular forms. Proteins become amino acids. Fats become fatty acids. DNA fragments into nucleotides. These molecules, once ordered and specialized, lose their complexity and begin to leak into the environment. Return to the earth. In burial or natural exposure, the body becomes food for microorganisms, fungi, insects, and other scavengers. These decomposers consume organic matter and transform it into carbon dioxide, nitrogen compounds, and minerals. Carbon atoms from your body re-enter the carbon cycle, absorbed by soil, consumed by microbes, or released into the air. Nitrogen from your amino acids returns to the soil as ammonia and nitrates, supporting plant growth. Phosphorus and calcium from bones gradually dissolve and enrich the ground. Nothing is wasted. Your body becomes part of ecosystems, feeding life that never knew you. A tree root may absorb nitrogen from what was once a muscle cell. That nitrogen becomes a leaf. An animal eats the leaf. The cycle continues. Even in cremation, though rapid and fiery, the same elements are released. Gases into the atmosphere, ash into the earth. Molecules scatter but are never lost. Atoms on the move. Atoms, unlike molecules, do not decompose. They change partners. They move through cycles. The carbon atom in your chest might have spent millions of years in rocks before becoming part of your body. It may now spend centuries in soil, then enter the atmosphere, then the ocean. Over time, your atoms may Be part of a blade of grass, then a grazing animal. Join a raindrop falling into a river. Drift in the atmosphere for decades. Be compressed into rock over eons. The scale is immense. Within a few decades, most of the matter that was once part of you becomes indistinguishable from the environment. Into the biosphere and beyond. The Earth is a closed system with respect to matter, but not energy. Your atoms remain on Earth for millennia, cycling through the biosphere, the interconnected web of living and non-living components. But not all atoms remain grounded. Some gases, like carbon dioxide and methane, rise into the upper atmosphere. They may be broken apart by sunlight, altered by chemical reactions, or even escape Earth's gravity over millions of years. Microscopic particles can be carried high into the stratosphere by volcanic eruptions or strong storms. Some are blown into space by solar winds, or carried as interplanetary dust. In rare cases, your atoms, carried by tiny particles, may leave Earth entirely, drifting through the solar system, eventually joining cosmic dust clouds orbiting the Sun. Joining the geologic cycle. Some atoms, like iron, silicon, and calcium, may become part of rock layers. Over geological timescales, they may be buried under sediment, melt in Earth's mantle, rise again in volcanic eruptions, solidify as new crust or crystal. These atoms may eventually be mined, reformed, or simply remain embedded in Earth's geological memory, unchanged for millions of years. Even bones, under the right conditions, can fossilize. In that state, the organic material is replaced by minerals, preserving shape but not substance. Your form vanishes, but your atoms persist. Stardust released, Stardust reborn. Earth itself is not permanent. The planet is dynamic. The Sun will eventually swell into a red giant, engulfing the inner planets, including Earth. If your atoms are still on this planet, billions of years from now, they may be vaporized, ejected, or incorporated into the debris of the dying solar system. That debris, composed of stardust, planetary rubble, and elemental ash, may drift through space for millions of years before collapsing under gravity again. New stars will form, new planets, new possibilities. Your atoms could someday become part of a star's core, join a comet's icy tail, settle on the surface of a new world, contribute to the chemistry of life elsewhere. The matter in you is not owned by you. It is on loan from the universe, borrowed for a brief moment to be organized as a person, and then returned to the greater cosmic system. Nothing is lost. There is no atom in your body that is new to the universe, none that will be destroyed after death. Everything you are, physically, is part of an eternal flow of matter. Death is not the end of atoms, it is a transition from one pattern, one configuration into another, from person to soil, from air to tree, from memory to molecule. The elements do not vanish, they scatter, they reunite, they reassemble into new forms, new functions, and new possibilities. The story of your atoms does not end with you. Chapter 10. Full Circle. The Stardust Within and Beyond. Some stories are not meant to end. They loop, evolve, and branch endlessly, much like the journey of atoms. In this book, we have followed matter from the heart of ancient stars to the breath in your lungs. But this story, as vast and complex as it is, leaves us with a profound truth. You are part of something immeasurably larger than yourself. When you touch your hand to your chest, you are feeling the architecture of hydrogen from the dawn of the universe, carbon forged in red giants, calcium shaped in supernovae. These are not metaphors or poetic ideas. They are scientific facts. You are, quite literally, the result of nuclear reactions that took place billions of years before Earth ever formed. Your body is a temporary expression of cosmic materials, shaped by energy, gravity, chemistry, and time. It is a structure built by molecules that were once unbound in deep space, and that will one day return to it. Every element in you has lived many lives, as dust, as rock, as living tissue, and it will go on long after you are gone. But the significance of this truth goes beyond matter. Every breath you take, every drop of water you drink, every piece of food you consume, they connect you to the planet, to the ecosystem, to the sun, and back again. The oxygen in your blood was exhaled by plants. The iron in your hemoglobin was born in a star's collapse. The calcium in your teeth once drifted in the ocean. You are not separate from the world. You're embedded in it, chemically, biologically, energetically. Even more so, you are not just part of the universe. You are a way in which the universe has become aware of itself. Your brain, that fragile network of carbon, oxygen, nitrogen, and trace metals, is interpreting this information now. It is reflecting on its own atomic heritage. That is not something rocks or gases can do. Life, and particularly conscious life, is the cosmos examining its own origin. You are stardust that can think. The continuity of existence. There is no single moment that defines the end of your atoms. They don't cease to exist, they move forward. After you're gone, the materials that formed you will scatter. Some will nourish a forest. Some may float in the air. Some may circulate through generations of other people. Your atoms may become part of a bird's wing, a coral reef, or a distant mountain. If that seems difficult to grasp, consider this. The atoms in your body today, right now, already come from countless other forms. Some were once part of dinosaurs, ancient bacteria, meteorites, volcanic plumes, or rain from the Pleistocene era. The atoms do not remember these past forms, but they were there. They played their part, and now they are playing yours. This cycle never stops, and it never wastes. A scientific legacy of belonging. In a time where many feel isolated or insignificant, the science of your atomic origin offers something incredibly grounding, a sense of belonging that is not abstract or spiritual, but material, tangible, and universal. You are not an accident. You are a product of cosmic necessity. Your existence follows a natural arc, from stardust to life to dust again. But it is filled with meaning, because meaning can arise from structure, complexity, and connection. In you, the cosmos became conscious, at least for a moment, and in that consciousness we find purpose. Not because the universe planned it, but because the reality of your existence is so unlikely, so temporary, and yet so interconnected, that it demands appreciation. The next time you look up at the night sky, remember, those stars are not separate from you. They are your relatives, your ancestors, your origin, and one day your atoms may float among them again. Final reflection. The story of Stardust is not only about the past, it is about the future. The atoms in you are still on a journey, and that journey is far from over. You are made of matter that has seen galaxies form and stars die, and someday it may do so again. So carry this knowledge with humility. Let it shift your view of yourself, not as small, but as part of a magnificent, ongoing cosmic process. You are made of stardust, and the universe, through you, remembers its own fire.